In this section, we are going to maximize linear programming problems with mixed problem constraints using the Big M method. The only condition is that the number on the right side of every problem constraint must be non-negative. Now, because we're going to see a mixture of less than or equal, greater than or equal, and equal signs in the constraints, we have to deal with each case separately. In a less than or equal constraint, we're going to add a slack variable to gain equality. In a greater than or equal constraint, we're going to subtract a surplus variable to gain equality. However, we're going to see in the very first example that if all we do is subtract a surplus variable, we are going to get a non-feasible solution. So to counter this, we're going to introduce an artificial variable to that constraint as well. Now, this artificial variable has absolutely no meaning in the original problem. Its sole purpose is to help us find a basic feasible solution so we can apply the simplex method. We have to be really careful to make sure the artificial variable does not become a part of the optimal solution to the original problem, though. So what we do is introduce a really large penalty to the objective function. We create this penalty by choosing a positive constant m so large that the artificial variable is forced to be 0 in any final optimal solution of the original problem. Then we add the term negative m times the artificial variable to the objective function for every artificial variable that we've introduced. We're going to use the same m for all the artificial variables. Now, since m can be as large as we like, when we're using a computer program, we just usually choose it to be the largest number that the computer can hold. To form the modified problem, first we have to make sure that any problem constraints that have negative constants on the right side get multiplied on both sides by -1 to obtain a constraint with a non-negative constant. So if the constraint's an inequality, that's going to reverse the direction of the inequality. Next, in any less than or equal constraint, we add a slack variable. In every greater than or equal constraint, we introduce both a surplus and an artificial variable. In any equal constraint, we introduce an artificial variable. And then for every artificial variable that we have added, we subtract m times that artificial variable to the objective function using the same constant m each time. Once we've formed the modified problem, we're ready to solve using the Big M method. Step 1, we form what is called the preliminary simplex tableau for the modified problem. And then in step 2, we use row operations to eliminate the m's that are in the bottom row of that tableau in the columns corresponding to the artificial variables. That's going to result in the initial simplex tableau. Then we solve the problem by applying the simplex method. We relate the optimal solution of the modified problem to the original problem. So if the modified problem has no optimal solution, that means the original problem has no optimal solution. We also have to pay close attention to the values of the artificial variables. So if all the artificial variables are 0 in the optimal solution to the modified problem, we just delete them, and that gives us the optimal solution to the original problem. However, if any of the artificial variables have a non-zero value in the optimal solution to the modified problem, that means the original problem has no optimal solution. So here you see a table of a summary of problem types and simplex solution methods. What we're working on in this video is number 3, maximization with mixed problem constraints. The right side constants have to be non-negative. the coefficients can be any real numbers, and those are the coefficients of the objective function. So for our first example, we're going to maximize p equals 2x1 plus x2, subject to the constraints x1 plus x2 less than or equal to 10, and negative x1 plus x2 greater than or equal to 2, and of course x1 and x2 are non-negative. So first let's just add slack and surplus variables to the constraints and see what happens. So the first constraint is a less than or equal, so to gain equality we're going to add s1, we're going to add a slack variable. So we get x1 plus x2 plus s1 equals 10. In the second constraint, it's a greater than or equal. So if we want to gain equality, we're going to have to subtract something. So we subtract a surplus variable. So we have negative x1 plus x2 minus s2 equals 2. Now, the problem is, in the basic solution, when x1 and x2 are 0, we can see in our first constraint that gives us an s1 value of 10. In the second constraint, when x1 and x2 are 0, we have negative s2 equals 2. So s2 has a negative value, but s2 cannot be negative. This is not a feasible solution, so this is where the artificial variables come in. So now we're going to actually form the modified problem now that we've actually seen the issue that we're facing. So the first constraint stays the same, x1 plus x2 plus s1 equals 10. But in the second constraint, we're going to add an artificial variable. So we have negative x1 plus x2 minus s2 plus a1 equals 2. Now, because I added a1, I'm going to subtract a1 from the objective. So my new objective function is p equals 2x1 plus x2 minus a1. And all of my x's, all of my s's, and my artificial variable are non-negative. Now to get this ready to put in a tableau, we need to solve our objective function, get it equal to 0. So we have negative 2x1 minus x2 plus ma1 plus p equals 0. So we use this to form the preliminary tableau. So constraint 1 gives us row 1. So our variables are x1, x2, s1, s2, a1, and p. And then we have our constant column. So row 1 is 1, 1, 1, 0, 0, 0, 10. Row 2 is negative 1, 1, 0, negative 1, 1, 0, 2. And the objective function gives us the last row. So negative 2, negative 1, 0, 0, m, 1, 0. Now the reason this is called the preliminary tableau is because it still has a non-feasible solution. If we look at this, we can see that s1 and s2 and p are the basic variables, but s1 has a value of 10 and s2 has a value of negative 2. So to get to the initial tableau so we can start the simplex method, we're going to get rid of the m's in the artificial variable column. So we're going to multiply row 2 by negative m, and we're going to add that to row 3 to get a new row 3 where the m will no longer be in the a1 column. So I can see that my new row 3 is m minus 2, negative m minus 1, 0, m, 0, 1, negative 2m. So this is the initial tableau, and I can see now that my basic variables are s1, a1, and p. So I want to solve this using the simplex method. So I look on the bottom row to the left of the P column and I find the most negative element. And that happens in column 2, negative m minus 1. So column 2 is the pivot column. That means that x2 is going to enter the basis. When I look in column 2 above the line, I see that both elements are positive, so I must compare the quotient to decide which one is my pivot row. So 10 over 1 gives me 10, 2 over 1 gives me 2. So row 2 has the smallest quotient, which means that's the pivot row. Now remember, in the simplex method, the pivot element needs to be a 1. In this case, we already have a 1 there, so now we're going to get zeros above and below. So using the command negative R2 plus R1 to get a new row 1, we see that we have negative times negative 1 plus 1 gives us 2. Negative 1 plus 1 is 0. Negative 0 plus 1 is 1. Negative times negative 1 plus 0 is 1. Negative 1 plus 0 is negative 1. Negative 0 plus 0 is 0. Negative 2 plus 10 is 8. So those are the values of row 1. Now, we also want to change negative m minus 1 to 0. So to cancel negative m out, we have to add m to it. To cancel negative 1, we need to add 1. So we're going to multiply row 2 by m plus 1 and add that to row 3. And you can see the computations for that over to the side. So my new row 3 becomes negative 3, 0, 0, negative 1, m plus 1, 1, 2. So now my basic variables are x2, s1, and p, where s1 represents row 1, x2 represents row 2, and p represents row 3. Now this tableau is not optimal because we have negative values in the bottom row to the left of p, so we choose the most negative, and that happens to be negative 3, so column 1 is the pivot column. So x1 is the entering variable. Now notice that above the line, only one row has a positive element. That negative 1 in row 2 means that it is not eligible to be the pivot row. So automatically row 1 is the pivot row. The pivot element in this case is a 2. I need to transform that to a 1. So I'm going to multiply row 1 by 1/2 to get a new row 1. So my new first row is 1, 0, 1/2, 1/2, negative 1/2, 0, 4. So now I just need to get zeros in the rest of the pivot column. So I'm going to use the commands R1 plus R2 to get the new R2, which is 0, 1, 1/2, negative 1/2, 1/2, 0, 6, and 3R1 plus R3 will give me my new row 3 of 0, 0, 3/2, 1/2, m minus 1/2, 1, 14. And we can now see that this tableau is optimal. So to find the solution for the modified problem, let's find the values of all of our variables. So x1 is a basic variable and it has value 4. x2 is a basic variable and it has value 6. s1, s2, and a1 are non-basic. They all have a value of 0 and p is 14. So this is a feasible solution because our x's and s's are non-negative and the artificial variable is 0. So now I can solve my original problem. I know that p reaches its max value of 14 when x1 is 4 and x2 is 6. In example 2, we're going to maximize p equals 3x1 plus 11x2, subject to the constraints x1 plus x2 less than or equal to 3, 2x1 plus 3x2 greater than or equal to 12, and x1 and x2 non-negative. So this looks very similar to the problem we just did, but we're going to see that it has very different results. So first we form the modified problem, and we do this by adding slack variables to less than or equal constraints, subtracting surplus and adding artificial to greater than or equal constraints, and adding artificial to equal to constraints. So forming the modified problem, the first constraint has a less than or equal, so we're going to add a slack variable to get x1 plus x2 plus s1 equals 3. The second constraint is greater than or equal to 12, so we're going to subtract s2 and we're going to add a1. So that becomes 2x1 plus 3x2 minus s2 plus a1 equals 12. And because I added an artificial variable to a constraint, I'm going to subtract m a1 from the objective. And x1, x2, s1, s2, and a1 are all non-negative. So to get this ready to go into a matrix, I need to rewrite the objective function. I need it to be equal to 0, but I need my p to stay positive. So I move everything to the left. So I get negative 3x1 minus 11x2 plus ma1 plus p equals 0. And now I'm going to use this and the rest of the modified problem to form the preliminary tableau. So my column labels are x1, x2, s1, s2, a1, p, and then I have my constant column because this is an augmented matrix. Row 1's values come from the coefficients of problem constraint 1. So we have 1, 1, 1, 0, 0, 0, 3. We use the second constraint to get the second row. So we have 2, 3, 0, negative 1, 1, 0, 12. And the objective we use to fill out the last row. So negative 3, negative 11, 0, 0, m, 1, 0. Now remember, this is called preliminary because this still does not have a feasible solution. We can see that our basic variables are s1, s2, and p. s1 has value 3, but that negative 1 in the s2 column gives us that s2 is negative 12, and that's impossible. So we're going to get rid of the m in the a1 column to form the initial tableau. So we multiply row 2 by negative m, add it to row 3, and that gives us a new row 3 with values negative 2m minus 3, negative 3m minus 11, 0, m, 0, 1, negative 12m. So now we can see our basic variables are s1, a1, and p. So to use the simplex method, we look for the most negative value in the bottom row to the left of the objective column. And so we see that that is negative 3m minus 11, and that is in column 2. So x2 is the entering variable. Now, above that bottom row, everything in the x2 column is positive, so we're going to compare the quotient to pick the pivot row. So 3 over 1 is 3, 12 over 3 is 4. So 3 is smaller, so row 1 is the pivot row. And the pivot element needs to be a 1. In this case, it is. So our next move would be to get zeros in the rest of the column. So we're going to use the command negative 3r1 plus r2 to get a new row 2, and that row would be negative 1, 0, negative 3, negative 1, 1, 0, 3. Now, to cancel negative 3m minus 11, I'm going to have to add 3m plus 11 to it. So I'm going to multiply row 1 by 3m plus 11, and I'm going to add that to row 3. And that gives me values m plus 8, 0, 3m plus 11, m, 0, 1, negative 3m plus 33. And you can see the calculations here to the side. Now, this tableau is optimal because there are no negative values in the bottom row to the left of P, so we can't choose a pivot column. So let's look at the solution to this modified problem. So x1 is 0, x2 is a basic variable, represents row 1, has value 3, s1 and s2 are 0, a1 is a basic variable, it represents row 2 and it has value 3, and p is a basic variable with value negative 3m plus 33. But we have a big problem here because the artificial variable is not 0. So this solution is not feasible. That means the modified problem has no optimal solution, neither does our original problem. So now we're going to look at an example where we have an equal constraint. So let's maximize p equals 4x1 plus 5x2, subject to the constraints 2x1 plus x2 less than or equal 24, x1 plus x2 equals 18, and x1, x2 greater than or equal to 0. So first, let's form the modified problem. So to the less than or equal constraint, we're going to add a slack variable. So we have 2x1 plus x2 plus s1 equals 24. The second constraint has an equal sign, so we add an artificial variable to that. So x1 plus x2 plus a1 equals 18. And because I added an artificial, I have to subtract m times that artificial variable from the objective. So my new objective function for the modified problem is p equals 4x1 plus 5x2 minus ma1. And x1, x2, s1, and a1 are non-negative. So let's get the objective function ready to go into the tableau. So we move everything to the left to keep p positive and to get 0 on the right. So we have negative 4x1 minus 5x2 plus ma1 plus p is 0. So we're going to use the modified problem to form the preliminary tableau. So in the preliminary tableau, row 1 is 2, 1, 1, 0, 0, 24. Row 2 is 1, 1, 0, 1, 0, 18. And row 3 is negative 4, negative 5, 0, m, 1, 0. Now notice, in this particular tableau, even though we have 3 rows, as of right now, we only have 2 basic variables, and those are s1 and p. So to get to the initial simplex tableau, we're going to get rid of the m in the a1 column. So we're going to multiply row 2 by negative m and add it to row 3. That gives us a new row 3 of negative m minus 4, negative m minus 5, 0, 0, 1, negative 18m. So now we see that we have 3 basic variables, s1, a1, and p. So let's apply the simplex method. Between negative m minus 4 and negative m minus 5, negative m minus 5 is the most negative. So because that occurs in column 2 is the pivot column, so x2 is the entering variable. Because all of the elements in that column are positive except for that last one, we're going to compare the quotients to choose the pivot row. So 24 over 1 is 24. 18 over 1 is 18. So that means that row 2 is going to be the pivot row. Notice that 1 is the pivot element, so my next move would be to get zeros in the rest of the column. So I'll use the command negative R2 plus R1 to get a new row 1. And that new row 1's values are 1, 0, 1, negative 1, 0, 6. Row 2 stays the same, 1, 1, 0, 1, 0, 18. And now to cancel negative m minus 5, I would have to add positive m plus 5. So I'm going to multiply row 2 by m plus 5, add that to R3. So that gives me 1, 0, 0, m plus 5, 1, and 90. And you can see the computations to the side. So now my basic variables are S1 representing row 1, X2 representing row 2, and of course P represents row 3. Because there are no negative values to the left of the P column in the bottom row, this tableau is optimal. So let's find our solution to the modified problem. So X1 has a value of 0, X2 is 18, S1 is 6, A1 is 0, and P is 90. So since my artificial variable is 0, my x's and my s's are non-negative, this is a feasible solution, so I can find the solution to the original problem using the variables x1, x2, and p. So I see that p reaches its maximum value of 90 when x1 is 0 and x2 is 18. Now this next problem we're going to form the modified problem for. We're not going to attempt to solve this. We have maximize p equals 2x1 plus 5x2 plus 3x3, subject to the constraints x1 plus 2x2 minus x3 less than or equal to 7, negative x1 plus 2x2 minus 2x3 less than or equal negative 5, x1 plus 4x2 plus 3x3 greater than or equal 1, 2x1 minus x2 plus 4x3 equals 6, and x1, x2, x3 greater than or equal to 0. Now remember, the only condition for using the big M method is that the number on the right side of the problem constraint has to be non-negative. So in constraint 2, I see that it is less than or equal to negative 5. The first thing I have to do is fix this by multiplying both sides by negative 1. So this changes all of my signs and reverses my inequality symbol. So my new constraint 2 is x1 minus 2x2 plus 2x3 greater than or equal to 5. So that's what I'll use to form the modified problem. So in my first constraint, it is less than or equal to 7. So I'm just going to add a slack variable. So I get x1 plus 2x2 minus x3 plus s1 equals 7. My second constraint is greater than or equal, so I'm going to subtract a surplus and add an artificial. So that gives me x1 minus 2x2 plus 2x3 minus s2 plus a1 equals 5. My third constraint is greater than or equal, so I'm going to subtract a surplus and add an artificial. So x1 plus 4x2 plus 3x3 minus s3 plus a2 equals 1. My last constraint has an equal sign, so all I have to do is add an artificial variable. So that becomes 2x1 minus x2 plus 4x3 plus a3 equals 6. Now, because I added artificial variables a1, a2, and a3, in my objective function, I'm going to subtract ma1, ma2, and ma3. So my new objective for the modified problem is p equals 2x1 plus 5x2 plus 3x3 minus ma1 minus ma2 minus ma3. And all of my x's, all of my s's, and all of my artificials are greater than or equal to 0.